Welcome back, everybody. Thank you for joining me. This is lecture 2 of our potentially very long series on homotopical topology. And in this lecture, we're going to talk about important topological spaces and also some constructions with them. Here are some of the takeaways that I hope you'll get from this lecture. The first is that many of the most important topological spaces come from Rn, Cn, and sometimes Hn in natural ways. We'll see a number of examples, like the sphere, Sn, disks, Dn, projective spaces, Rpn, Cpn, and Hpn, the Grassmannians, Gnk, Stiefel manifolds, V, and excuse me, I'm actually going to do a different naming convention and call these GKN, the Stiefel manifolds VKN, flag varieties Fn, K1 up through Km, groups, the orthogonal groups On, special orthogonal groups SON, unitary groups UN, special unitary groups SUN, and the symplectic groups SPN. Alright. Takeaway 2 is that there are a number of important constructions one can do with topological spaces, such as some that you may be familiar with, like the product X and Y, mapping cylinders and mapping cones, so CYLF of a map, CF of a map, suspension, sigma, wedge sums, smash products, mapping spaces, path spaces, loop spaces. And many of these constructions, they tend to have interesting universal properties. All right, let's begin with part 1, which I'll just call a bestiary. Of topological spaces. All right. many of these should be review for some of you, but we'll make sure just to fix some notation. All right, so our first definition. Let n be some natural number. The n-sphere, an Sn, is going to be the subspace points x in Rn plus 1 with magnitude 1. All right, so an example. This is R2. The one sphere is the circle that you know. In R1, the zero sphere is just 2 points. It's just 2 points. All right, similar type of definition. The n-disk dn is going to equal the set of all x in now Rn, such that the magnitude of x is less than or equal to 1. So, for example, the 2 disk is everything in here, and the 1 disk is everything here. So more generally, we have that the n-sphere is equal to the boundary of the n plus 1 disk. Great. Next up, is a topological space whose utility we might not fully understand until later in the course. Again, let's take a natural number n. The standard standard topological n simplex, which is written delta n. It's defined as a subspace, once again, of Rn plus 1. And the definition that delta n is going to be the set of all tuples x0 through xn in Rn plus 1, such that all of the xi are non-negative, and the sum of all of the xi is equal to 1. Oops. No, they're not all greater than or equal to 1. They're all greater than or equal to 0, and the sum of them is equal to 1. So what does this look like? Let's give another picture on the side. I'll first draw the 1 simplex. So this here is R2. The 1 simplex is going to be all those points between the x and y axes that lie on that line. So this is delta 1. Note that delta 1 is homeomorphic to the one disk, but it comes with a specific embedding into R2, whereas the one disk comes with a specific embedding into R1. Good. Next up, we have a big class of examples that are really, really important. And we'll need to give an a definition for each one, each field, the real numbers, the complex numbers, and the quaternions or Hamiltonians. Okay. So let's take an integer greater than or equal to 1. Then, first of all, the real projective n space, sometimes called the projective space of the real projective space of dimension n. This is written the blackboard bold R, blackboard bold P, n. Sometimes you might see it as blackboard bold R and then normal P to the n, or if you're hanging around with algebraic geometers, you'd see blackboard bold P, the subscript R, superscript n. So you may see any one of those. It should be pretty clear that we're talking about projective space. So this is going to be a quotient space. Well, there are a number of ways we can present it, but so let's say for the time being that Rp to the n is going to be the set of lines through the origin. In R to the n plus 1. Now, of course, equivalently, a line through the origin is a one-dimensional vector subspace. Of R to the n plus 1. So if you've never seen projective spaces before, it'll be very important to take a look at an example. So every line in the plane that bugs me. Let me draw this so it's more even. So every line through the plane, every line in the plane that goes through the origin is determined by a length 1 vector, so a unit vector. But it's not uniquely determined by that unit vector, because there's another unit vector pointing in the other direction. So this allows us to present Rp1, which is which consists of one-dimensional vector subspaces of R2. So Rp1, we can present it as, well, the unit circle is a circle. So Rp1 is going to be the quotient of S1 by the equivalence relation that sends x to minus x. Now this quotient is just homeomorphic to the circle itself. So Rp1 is a circle. Next up, we have, well, complex projective n space. There are fireworks going on outside. Now this is denoted CPN, and similarly you might see bold C regular P n or P subscript C to the n, or if you're working with classical algebraic geometers, you'd just see P to the n with the C implied, but let's not worry about that one for now. And this is defined identically. It's defined identically to RPN. With CPN, it's going to be lines, but now they're complex lines through the origin. In, C to the n plus 1. And you can guess what the next one will be for quaternionic projective space. And that's, of course, denoted H, P, N. And I'm gonna make sure to write this in the vector space, vector subspace definition, because, well, the quaternions H are not a commutative algebra. They're a division ring. And so we have to choose whether we're talking about left modules or right modules in terms of subspaces, in terms of vector spaces. So free modules, but are they left or right? So we're just going to choose one-dimensional left submodules. Of H to the n plus 1. Great. Now, similar to how we could identify RP1 with the circle, we can in fact identify CP1 with the sphere, S2, and we can identify HP1 with the 4 sphere, S4. Let me now just focus on real projective space. For simplicity's sake, all of what I'm about to say ports over without any modification to the cases of CPN and HPN. So there's a standard notation for points in RPN. And these are called homogeneous coordinates. And what they say is, so a point in R to the n plus 1 lies on a unique line through the origin. So if we have a point x0 up through xn in R to the n plus 1, this will give us a homogeneous coordinate written x0 colon to xn in square brackets. And so this is just defined to be the equivalence class. of that point. All right. So all of the spaces that we introduced, all the topological spaces that we introduced already, come in infinite variants. And so let me say, so first of all, there's a map from R to the n, including into R to the n plus 1. And this just takes x0 up to xn minus 1 and maps it to x0 up to xn minus 1, comma 0. So that's a standard inclusion that we have there. And this gives us a chain of, say, R0, including into R1, including into R2, and so forth. And we can take the union of this whole chain. The union is going to give us a space that we can call R infinity. And instead of a union, I'm going to write colim, and that's notation that will become clearer after next lecture. So, by colimit, I just mean the increasing union. And so this R infinity, well, a point in R infinity will be a sequence, say, xi, for natural numbers I, where xi equals 0 for all but finitely many I. So that is to say that every point in R infinity in fact lies in R to the n for some big enough n. All right. So, with induced by the inclusion, say, Rn into Rn plus 1, this takes the circle Sn minus 1, or the n minus 1 sphere, into the n sphere. So that is to say that this map factors. And it says an inclusion. And this is what we would call the inclusion of the equator. Okay, and so just as before, we can define the infinite sphere, S infinity, to be the colimit of that tower. 0 into S1 into S2, etc. There's a similar construction, of course, ditto for the disk D infinity. Okay, so now we can make things a little bit more interesting, which is to see that this inclusion of Rn into Rn plus 1, well, it takes any one-dimensional subspace to another one-dimensional subspace. And in fact, it's essentially the same subspace, just with the 0 in that coordinate. So what this means is that, in fact, we also get a map from Rp to the n minus 1, including into Rp the n. And so from there, we can define Rp infinity as the colimit of that tower. Ditto with Cp infinity. Cp infinity is a very important space. Well, to be fair, we don't care that much about it as a topological space. We care about it a lot up to homotopy equivalence. And that's something that we'll talk about in 2 lectures from now, so lecture 4. And we care about this because someone would say that Cp infinity is a KZ2. And I won't explain exactly what that means right now. Now we're going to go into a really important class of generalizations, very wide generalizations of projective space. These are going to be the Grassmannians. So let's take 2 integers, k and n, both greater than or equal to 0. If they're both equal to 0, it's a little bit, actually if either of them is equal to 0, not super interesting. But alas, the Grassmannian GKN is, as a set, the set of all vector subspaces of Rn of dimension k. There are a number of ways to topologize this to make it precise, but loosely speaking, the topology is such that points are close if the angles between the corresponding vector spaces are small. So, important examples. Oops. Let me back up and also just say that technically I'm just defining the Grassmannian over the reals. You could equally well define the Grassmannian over the complex numbers and over the Hamiltonians, over the quaternions. So, okay. One example, G1, n is just by definition equal to Rp n minus 1. Okay. G0, n. Well, how many zero-dimensional subspaces are there? Well, this is just one point. An important example is by taking orthogonals so that is the map that sends a vector space V to the space of all W in Rn such that W dot V equals 0 for all V in V. So that's that function. By taking orthogonals, there is a homeomorphism of GKN with Gn minus Kn. That's a very important example, and a very important homeomorphism. I'll put that in a box because it's important. All right. So let's take another definition. Along the same lines as the infinite stuff that we did up here. Excuse me, my iPad was glitching a little bit. So the first thing we can say is that the standard inclusion again of Rn into Rn plus 1 induces an inclusion of GKN into GKN plus 1. And so this continues. We can take the colimit and get something that we might call GK infinity. Next, there's another inclusion that we can consider, which is given a vector space V sitting inside Rn, we can map into Rn plus 1 and take V to V cross R, where we get now a k plus 1 dimensional subspace. So what this gives us is an inclusion of gk comma n into gk plus 1 comma n plus 1. And that gives us a tower. When we take the colimit of that, we get something that's worth being called G infinity infinity. So how can we interpret points in here? Well, a point in G infinity infinity is a subspace, a vector subspace, of R infinity of infinite dimension but such that there exists some finite dimensional V such that X is equal to V cross. I'm going to write this as R infinity minus the dimension of V, but all I mean is that it's V cross in the dimension of V plus 1 up to infinity factor. Copies of R. So all of these like unions of these directed inclusions, there's always still some finiteness condition that while the elements can be of arbitrarily high dimension, they're still finite dimensional in a certain sense. All right. There's one more thing that I want to say about Grassmannians, but we'll hold off until 2 or 3 lectures from now. So one thing you can wait for is a really, really cool stratification or division of Grassmannians into what are called Schubert cells. These are really important in algebraic geometry and combinatorics. It's a super cool thing, but we're going to wait until we have a reason to talk about what are called cell complexes, and then the Grassmannians are going to be really cool examples of cell complexes. Let's get one more generalization. So instead of just looking at a single k-dimensional subspace, we can look at chains of subspaces. So let's take integers k1 strictly less than k2, so forth, strictly less than km, strictly less than n. So note in particular that m here, m is at most n minus 1, otherwise there just are too few places between 1 and n to fit all those k's in there. Okay, so we're going to define the Flag manifold written f n semicolon k1 up through km, or perhaps to be more consistent with my Grassmannian notation, I'll reverse those and write k1 up through km semicolon n. So this is the subset, or is the set of tuples v1, v2 through vm, where v sub I is a subspace of R to the n, and the dimension of v sub I is equal to k sub I. So these k's are controlling what the dimensions of these vector spaces are going to be. And a chain of vector spaces like this is called a flag. So a special case very important case is if k1 equals 1 and k2 equals 2, and in general ki equals I all the way up to kn minus 1 equals n minus 1, then we call f of, I guess, 1, 2, up to n minus 1, n is called a complete I guess it's the complete flag manifold in Rn, or maybe I should say of Rn. And here we would write just simply Fn. You can topologize this in a number of ways. One way to topologize the general version is to consider it as a subspace of GK1, n cross G of K2, n, and so forth. So that's a possible way to topologize it. All right. Now let's go on to a different class of examples that are going to be extremely important throughout homotopy theory, and indeed throughout many areas of mathematics. So much so that you've probably already encountered many of them. All right. We'll give a definition in 3 parts. So, first of all, let's fix an integer n greater than or equal to 1. The orthogonal group O of n is the topological space of orthogonal matrices of n by n real orthogonal matrices. Recall that a matrix M is orthogonal if the product of M with its transpose equals M transpose times M equals the identity matrix. Now, furthermore, the special orthogonal group SON is the subgroup of O of n on those matrices with determinant 1. Next up, we do the same thing, but over the complex numbers. So the unitary group UN is the topological space. Really, it's a topological group under. This is also a topological group under matrix multiplication, is the topological space of n by n complex unitary matrices. So again, let's remember that M is unitary if when you multiply M with its conjugate transpose, calling M upper star, this is equal also to M upper star times M equals the identity. So M is the conjugate transpose, which again, which as should be a reminder, is where you take the transpose of each complex number, and then you take, you take the conjugate of each entry of the matrix, and then you take the transpose. Then there's identically the special unitary group, SUN is the subset O of n on the determinant 1 matrices. And finally, we have the symplectic group. SPN. And this is the topological space of n by n quaternionic unitary matrices. And here, what I mean is the quaternionic the quaternionic conjugation takes I to minus I, j to minus j, and k to minus k. So it's the same sort of thing. All right, so these are extremely important groups that will come back over and over and over again in many different conjugations. Let's give one final important example of topological spaces that show up in nature. This is related to a bunch of the previous examples. So first of all, let's remember that an orthonormal K-frame in Rn is a choice of K vectors V1 through Vk that, let me say, it's a choice of K unit vectors, so vectors of length 1, that are all mutually orthogonal. In that the dot product of Vi dot Vj equals 0 for all I and j. The set of these carries a natural topology, and this topological space is going to be called the Stiefel manifold. Stiefel manifold, written VKN, is going to be a set of all orthonormal K-frames in Rn, topologized as a subspace of Rn cross itself K times. So the Stiefel manifold, this carries a natural action of the orthogonal group OK by acting just on the vectors in that K-frame. And furthermore, there is a surjective map from Vkn onto the Grassmannian Gkn, witnessing witnessing GKN as the group quotient. It's the group quotient of VKN by the action of the orthogonal group. And because the orthogonal group acts continuously, and in fact it's a topological group action, we get a topological space back. All right, this brings us finally to section 2 of our lecture, constructions with topological spaces. So I first want to start with a proposition. Let's take two topological spaces X and Y. And we can consider their product. It has the following universal property. This property is that given any topological space Z, and any continuous maps F from Z to X and G from Z to Y, then there exists a unique continuous map from Z to X cross Y. We can call this F cross G. There's a unique continuous map F cross G, making the diagram commute And what is the diagram? Well, the product of X and Y projects onto both X and Y. And this map we usually call pi sub X, pi for projection. Similarly, there's a pi sub Y. And if we're given Z together with a map to X and a map to Y, this map is F, this map is G, then there is a unique continuous map here. And this is the map. I'm trying to be a little too fancy with what I'm drawing, F cross G. So there's that unique map that makes this diagram commute. So let's prove this. It's not a particularly difficult proof, but I think it's important to see how this line of reasoning works. So there's an obvious choice for this map for F cross G. And what it should do is it should take a little z in Z to the pair of F of Z comma G of Z. And so that's our obvious choice. And in fact, if this map really is continuous, then it is the unique such map. Actually, that's actually very poorly phrased logic. So this is the obvious choice. Let's first show that this is continuous. Well, what we need to do is we need to check that open sets in X cross Y pull back to opens in Z, and open sets in X cross Y are generated by the products of open sets in X and Y. So a basis element would be open in X cross an open in Y. So I want to see what happens. So what happens when we take F cross G inverse of something in there? Well, it's going to be some x, little x comma little y. Sorry, this is a very a poor way of phrasing this. So F cross G inverse of U is going to be the set of all Z such that F of Z is in U sub X and G of Z is in U sub Y. Oops. Is in U sub Y. So in other words, this is F inverse of U of X intersect F inverse of U of Y. Excuse me, G inverse of U of Y. And because F and G are both continuous, this is open in Z. All right. So F cross G is continuous. Why is this unique? Why is this unique? Well, suppose we have any other H. Suppose we have some H mapping to X cross Y. That works. Then, because the diagram commutes, H composed with pi sub X equals F, which means that H of little z is going to equal F of little z comma something, and similarly pi y composed with H equals G, so H of little z is going to equal something comma G of little z. Well, that just gives us that H equals F cross G. And so it's unique, and we can put a QED there. So that's just an example of a universal property of a construction with topological spaces. Once we learn about category theory, we'll be seeing universal properties all over the place. Now we'll just quickly go through some important constructions. So let X be a topological space. The suspension of X written capital sigma X is the quotient of X cross the unit interval 0 to 1 by the equivalence relation where little x 0, comma 0 is equivalent to little bad choice of notation, where little x, comma 0 is equivalent to little y, comma 0 for all x and y in X, and little x, comma 1 is equivalent to little y, comma 1 for all x and y in X. So what does this look like? Let me just clean that up a little bit. Well, if that's our X, the suspension is what's gonna happen when we take a point and connect it to every point in X, and another one and connect it to every point in X. So this pictorially shows us that the suspension of the circle S1 is homeomorphic to the sphere S2, and more generally, an easy exercise is to show that the suspension of Sn is homeomorphic to Sn plus 1. This is very important. Great. As a quick aside notation, we'll write I for the unit interval 0, 1. That's just to keep things a little bit more organized. All right, another definition. Let's have a map F between topological spaces. Then make two definitions. The mapping cylinder written CYL sub F is the quotient space of, first of all, we take X across the unit interval, disjoint union Y, and then we mod out by the equivalence relation where X, comma 1 is equivalent to f of X for all X in X. You could also equally well choose 0 instead of 1 for this endpoint. Next up, and what we'll see more frequently, the mapping cone C sub F is now going to be the quotient space of the cylinder by the relation where x, 0 is equivalent to x prime, 0 for all x and x prime in X. So if we have a pretty straightforward map, so let's give an example. Where our map F is going to be S1 including into R2, then our cylinder, this is going to be F, our cylinder, CYL, F. What's that going to look like? Well, that's going to be, we have a real plane here. This, of course, goes out infinitely in both directions. We have our circle, S1, and it's glued as a cylinder. So that's why it's called the mapping cylinder. All right, and the cone is going to be the same thing. Circle here, but where we've identified all of the points at the top of the cylinder. So all of these points get smushed down to that one point here, which means that we look like this. So another example is we can take a look at the identity map on a topological space X. This gives us that the cone of F is just X and a point on top of it. Then we can look at the inclusion of X into the cone on F, that, let's say, into the cone on the identity of X. And this is going to be the map called this will be the map called x, 1. Right? Is that how I chose? Yeah, that's how I chose things. And so then the cone on the map x, 1 is going to be the suspension of X. So cones are strictly more general than suspensions. Great. So we'll give another definition. A pointed topological space is a pair x, little x0, where x0 is in little x. A pointed map between spaces, pointed spaces x, little x0, and y, little y0, is, well, it's a map of topological spaces x to y such that f of little x0 equals little y0. More generally, if x, a is a pair of a topological space X together with a subspace, and y, b is the same with B, a subspace of Y, then a map of pairs from x comma A to y comma B is a continuous map f from x to y such that A maps into B. So, meaning f of A is a subspace of B. So let's just note that being a map of pairs is a condition on a map f from x to y, not additional data. Meaning there's no additional data required to specify that a map preserves a certain subspace. All right. Here are two more definitions. Let's take two-pointed topological spaces. First things first, the wedge sum. Written x, wedge, y. This is, of course, an abusive notation because we've left out the points x0 and y0 from the notation. So, depending on which choice of points we have, we could potentially get different answers, but this should be clear enough in context. So the wedge sum is going to be, can be described in two different ways. First, it could be the quotient space of, take the disjoint union of x and y, modulo x0 is equivalent to y0, or we could view it as a subspace of the product it's the subspace on those points where either x0 is in the first coordinate or y0 is in the second coordinate. Or both. It's not an exclusive or. So, these are clearly equivalent characterizations. This second characterization will allow us to define something else, and also very important, the smash product. X. This is read as x smash y, and that symbol is in LaTeX \wedge. This is defined as the quotient space of x cross y, quotient x wed. Sorry, I know this is really confusing. This is, in LaTeX, the smash product is \wedge, and the wedge product, the wedge sum, is \v. I know it's confusing. So we take the wedge sum of x and y, and we can quotient the Cartesian product with the wedge sum, and that gives us the smash product. So let's take a look at an example. Let's take, very simply, let's let x, change back to white, let's have x be the circle S1 with any chosen base point. It doesn't matter because it's path connected. And y, let's have y be the interval with 0. So the wedge sum, x wedge y, what will that look like? Well, it'll look like a circle and a line hanging off of it. The smash product, what will that be? Well, we'll take the product, the Cartesian product, first of all, which is that cylinder. And this line is the pair x0, comma, I. Let me draw this in a different color to make it clearer. This circle here is S1, comma, 0. So what's the quotient space when we quotient out? Well, it's going to look like first the cone here, and then quotient and collapse this line to 0, which just gives us the disk. All right. We're nearly done with this lecture. We'll introduce that's not how you spell definition. Definition. Let x and y be topological spaces. The mapping space written C of x, y, this is the mapping space from x to y, is, well, as a set, C of x, y is just the set of continuous functions. But the topology is interesting. With the topology generated by following basis. So for K, a compact subset of X, and O, an open subset of Y, we let U of K, comma O equal the set of F such that F of K sits inside O. And so we let U of KO be the basis, and so this is called compact open topology. Great. So specific examples. There are two really important specific examples. So when X is the interval, this space is called the path space of Y and is written P of Y. When X is the circle, C from X to Y is called the loop space of Y and is written omega of Y. I'll leave you off with an important lemma that I won't prove, but you should feel free to either try to prove yourself or look up a reference. So let X, Y, and Z be topological spaces suppose that X and Y are Hausdorff and X and are Hausdorff and locally compact. Then we have a map from the mapping space of X into the mapping space from Y to Z. Now this maps via the map that takes a map taking little x to f sub little x from Y to Z. This will go to the mapping space from X cross Y into Z. This gives us now the map that takes little x comma little y to f sub x of y. And the lemma is that this map is in fact a homeomorphism. So I will leave that up to you to take a look at to find a proof for yourself. And in our next lecture, you should get excited for some category theory, which I find quite fun. I hope to see you there later.